In this session, we are going to give an introduction to the two-dimensional model hydrobit flood. The presentation will be divided in two main parts. First, we're going to look at how to use hydrobit flood model to simulate floods, starting by making a comparison with one-dimensional models. Then we're going to see the basic information that is required to run the model, calibration and validation process, integration of hydrological and hydraulic processes as well. The second part will be an overview of the QGIS base user interface with an introduction to the hydrobit flood plugin and the graphical interface based on QGIS. Then we'll end up by providing a few examples of the application and output of hydrobit flood. And we also have a question and answer period at the end of the presentation. The traditional way to make hydraulic modeling was by using one-dimensional model. The one-dimensional models were very popular during the 80s, 90s, and most of the 2000s. And during that period, the two-dimensional models were, for the most part, most expensive to use. They require a lot of computer power, and sometimes users didn't have the data to support the two-dimensional approach. And the issue with one-dimensional models is that they only provide a constant water surface elevation on a given cross-section. They work by cross-sections, and also the velocity on the whole cross-section is uniform. So there is no variation of the velocity calculated on a given cross-section. The other assumption that is made on one-dimensional models is that the flow is one-directional. That means that as soon as you locate a cross-section on a given river, then you are essentially forcing the flow that will be calculated perpendicular to that cross-section. So by drawing the cross-section, you are essentially deciding what will be the direction of the flow in that area. The third assumption is the neglection of exchange or momentum exchange between the main channel and the floodplain. So there is no momentum exchange between the main flow area and the floodplain, which is something that may be important, particularly during rapid floods. The basic equations are the continuity equation shown in the first one here, and the momentum equation in 1D. And I will not get into the details of these equations, but I just wanted to point out that the main unknowns in these equations are the area of flow and the discharge of or flow rate on a given cross-section. And that is why these two variables essentially define the whole hydraulics in a given cross-section. The other thing that is important to keep in mind in 1D models is that in between one cross-section here and the next one, the assumption is that there is a linear variation of the topography. So there is no detail of what's going on between two lines. Now the 2D approach is very different, because the 2D approach assumes that the flow velocity can vary in space and time, and the depth can vary in space and time as well. So it's not restricted to cross sections. It varies continuously in the flow field. The equations are also the continuity and momentum, but instead of having one equation, we have two equations now that corresponds to the depth of flow and the two components of the velocity vector. The main assumption in 2D models is that the velocity does not vary in the vertical. So they assume that we have a vertical integrated velocity that does not vary with depth. So that's the main assumption in 2D models. There is also, this assumption leads to a limitation that there is no consideration for secondary currents, which may be an issue in sharp bends in river. So if you have a bend in a river, normally there occur secondary currents, and that may have an importance there, particularly for the sediment transport processes. And also, the friction is based on Manning's formula. Now, the perspective that a 2D model sees is completely different from what the cross-sectional perspective of 1D models that we showed before. So you have the terrain can be actually three-dimensional, and the model generates a mesh. In this case, it's a flexible mesh, as the one used in the hydrobit flood model. And at each cell of this mesh, the model determines the velocity and depth of flow. So there is no concept of cross-sections here. You can extract cross-sections, as we will see from the results, but these are not part of the actual computational process. In the flexible mesh, as in the hydrobit flood model, we have triangles that can vary in size, and also they can adapt to different geometries, for instance, in this case, around buildings. And that allows to generate velocity fields that are very complex and adapt to the flow around the structures. As you can see here, every arrow that you see here is a velocity vector calculated at each of the triangles that you see over here. So it's a much more flexible method than the 1D approach. Now, the 2D models are not without limitations, because the fact that you cannot have vertical accelerations in the flow makes difficult to deal with this type of structures, like a morning glory spillway or this other spillway here, where you have a very high velocity, vertical velocity. However, for this type of structures, the model can use localized components that account for the actual computation of flow in these structures, overcoming in that way the limitation of the vertical acceleration for the 2D models. So when is a 2D approach adequate to simulate hydraulic processes? Well, when you have confined flow, so if you have a river that is confined and you don't have overflow into the floodplain, or if the floodplain storage is very small, or when you are sure that the flow is essentially one-dimensional, it's only going in one direction or one way, and there is no need for detailed velocities, but you consider that having the average velocity in a given cross-section is small, is okay. So this typically occurs when the cross-section width is relatively narrow. Now, when it's not suitable, and it's more recommended to use 2D models, is when you have branching river and unconfined flow. When the detail of floodplain is important, you need to have a detail of what's going on there for either for flooding purposes or planning, or for sediment transport, where the flow patterns are non-uniform, where the velocities are not perpendicular to any cross-section, or they can vary during the simulation. When you have complex channel floodplain interaction, and when preparation of hazard mapping and definition of the risk associated with the flood is important. Now, I will show you an example of when a 1D approximation would fail. What you see here is the superposition of a set of cross sections corresponding to the HEC-RAS 1D model, and in the back you have velocity vectors obtained by a two-dimensional approximation of a model, and it's actually a river flow 2D application in the same river. So you have a river that branches out here and comes downstream in this direction. But then the river overtops its banks and then gets into the floodplain. And all these vectors that you see here is what they show, that the flow is coming into the floodplain. Now, what happens is that in the 1D model, you wouldn't even consider that this happened, because the model will only be restricted to the cross sections here. And it would ignore that this situation happens as it's simulated by the 2D approach. The other thing is that in this point here, if you see the 2D model indicates that there is an overflow on the bank here, and then the actual flow is coming upstream in this direction. So it's coming downstream here, overtops, and then it flows in the opposite direction here. That would be completely impossible to obtain in a 1D model. The other thing that this is assumed that on that area that you see more detail what's going on here. The other thing that happens in 1D models that can, as I mentioned, the assumption is that the flow is perpendicular to the cross section. So you have here this cross section, and then for the most part the flow is perpendicular, and that would be okay. But look at what happened here. This cross section, the flow is, in large part of it, is almost parallel to the cross section. So it's completely violating the assumption of perpendicular cross section to the 1D approach. Of course, the model will give you some results, but the results may be completely unrealistic because of the violation of all the assumptions that may occur. So the main advantage of using a 2D model is that you don't have to pay attention to those details, because if you refine the mesh reasonably well in the floodplain, the actual model will tell you where the water is going to. Okay, so the other thing that can happen, and this is something that happens very often, is that you make a simulation with 1D model for low flow, and then you design your cross sections as shown in this plot here, that more or less follow the correct direction of the velocities for low flows. Now, since you cannot change the orientation of the cross sections through the hydrograph, when you compute the full hydrograph, it may happen that for the peak flows, the flow may actually overtop everything, and then it goes through directly to the floodplain, and it flows in one direction, essentially going downstream. That would require having cross sections that are in different orientation to avoid the violation of the assumption of perpendicular flow to the cross section. But that is obviously not possible, because you cannot change the direction of the cross sections dynamically in a 1D model. Now, the other thing is that in a cross section, in a 1D model, the water surface elevation shown here in green is constant. So you cannot have any variation. The results of a 2D model indicates that it can vary in the cross-section here, and it can even have water in areas where the 1D model would not give you any flooding at all. Now, look at the width of this cross-section. It's about 7,000 feet wide. That means that you have way more than 1 mile wide cross-section, which is obviously something very, very extreme to have a one-dimensional approximation, considering that everything would be uniform on that wide cross-section. Now, as a conclusion of whether using 1D or 2D model, there are situations where, as we discussed, that 1D models are applicable. However, if the flow is really 2D, no matter what you do, you won't get good results with a 1D model. So it's nowadays, with the development of these tools like HydroBidFlood and the computers that we have available nowadays, there is no reason to use the simplified approach. And that's why, whenever you have storage areas that are important, where the elevation of water surface is not constant in cross sections, threaded river, or when you want to develop hazard map with certain detail, then it is obviously the recommended way. And that's why we developed the HydroBidFlood model. Now, in the HydroBidFlood, as we will see, we need to generate a mesh, and the mesh needs to be confined to an area. So we need to define what will be the area of flow. And we do that in a layer that we'll see later that is called the domain outline. That indicates the extent of the area that we want to model. Now, one thing to take into account is that we don't know in many instances how big this area should be. So the idea is that we should start by using a relatively big area in order to compute the flow, make simple runs initially just to see if the flow can get to the boundaries. And if the water hits the boundary that we have selected, then we should extend the mesh down, even out of that area. So the only areas that we recommend that the water should touch from the boundary of the mesh are those areas where the flow either gets in, the inflow areas, or the outflow areas. These are the only two areas of the boundary where we recommend having or allowing the water to get in. Because otherwise, the assumption is that you have like a wall that surrounds the mesh. So this is something that we will have time to evaluate during the practical exercises that we will have through the course. Now, one of the fundamental data that we need to run HydroBidFlood is the topographic data. It's probably the most important factor in applying the model, since it has the greatest impact on the model results. So the surface over which the water flows is that terrain, and as we will see in the next session, we need a digital elevation model for that. And that digital elevation model should cover a greater extent than the area of interest. So what you see here on the right is a digital elevation model where the colors indicate the terrain elevation. So the darker areas here in brownish are higher, and then you have a river with light green colors here. Now, we will cover this, but you need to be aware that sometimes the digital elevation models that are generated by some techniques like LiDAR and even satellite include artifacts that contain part of the man-made structures like bridges, for instance. You see here. So this is a bridge that of a road that crosses this river, and we need to make sure that this is removed from the digital elevation model, because otherwise this will be considered like a dam here. And you see here in this one, in this part here, it has been removed, this other bridge here. So this is okay, this is not okay, and this is also another one that is not okay. So if you were to use a 2D model here, like hydrobid flood, what would happen is that the flow will find this bridge and then over top and go all over the place, and it will not give you good results. So you need to verify bridges, channels, and any other hydraulic structure that would be included in the topographic data. But it is the topographic data, I would suggest, that is the most important piece of data that you will require to use and apply hydrobid flood. Another thing to remember is that you need a projection and a datum to apply the hydrobid flood. And as we will see in the next session, all the layers that we construct in the QGIS interface need to be in the same projection, because they need to be related to each other, and in order to be related correctly, they need to be in the same projection. So you need a horizontal projection. The model doesn't work with latitude and longitude, it works with plane projections, and the QGIS interface provides a wide variety of projections that you can use and you can convert if that's necessary. Also, the vertical datum that you use to indicate the elevations of the terrain and so forth needs to be the same. And otherwise, they will need to be converted to the same datum for all the layers that are in the QGIS system. So we will see that we will need to use a standard projection, not a local projection or arbitrary one, in order to the hydrobid flood model to work properly. So we need topography, we need to set a projection, and we need boundary conditions. What are boundary conditions? Well, boundary conditions are the data that we impose on the boundary at inflows and outflows to the mesh. So the boundary conditions are the one that indicates the flow rate that comes from the river upstream, or how the flow behaves at the downstream condition. So you need to, if you use the model as a hydraulic model, you need like an inflow hydrograph similar to the one you see here, where you have a variation of discharge with respect to time. And that will be the discharge that will enter by the inflow condition to the mesh. Now, remember that you can also, as we will see, you can use the model also as a hydrologic model, where you would not need a boundary condition like this per se, because you would generate a runoff that will end up generating its own discharge. So we'll have to keep this in mind. Now, we'll see that when generating the mesh, as we said, is formed by triangles, but you can refine the mesh in many different ways. So if you have a channel or a main channel in the river, you have tools to make the mesh within this channel much dense. So you have smaller cells that improve the accuracy of the simulation within the channel. And then you have larger cells in the floodplain where maybe you don't need that type of resolution. So in those cases, there will be a variation of the size of the cells, of the triangular cells, between the high density lines and the larger areas where you have much larger cells. So it is recommended that you would not have a change rate that is bigger than 2:1. So if you have, let's say, an element that has 10 square meters in one location, you don't want to have the neighbor element here, you don't want it to be more than 20 square meter or so. So this is approximate, of course. The better, the closer you are to this ratio, the better your results. And we will have time to play with this resolution changes. Also, you have a way to locate cells. So if you want to refine, for instance, the mesh along a canal, you have tools that we will teach you to use that allow the mesh to be aligned to the canals or to any other feature in your urban environment. So far we have seen topography, we have seen the importance of the boundary conditions, of the mesh, and then we have the terrain roughness. So the flow occurs over a terrain. It is not the same to flow over a terrain that is covered by asphalt or a terrain that is natural and is covered by certain vegetation. The coefficient that represents the terrain roughness is called the Manning-Sen. Manning-Sen is a coefficient, an empirical coefficient that you have to set, and it can be varied in space, but it represents how rough is the terrain. And you have values here that range from, let's say, you see here for asphalt and concrete is 0.02, and it can get up to 1 or so in that range for very dense turf. And this table are recommendations, general recommendations depending on the terrain coverage, and you can adjust these empirical parameters. It's part of the calibration process, as we will see, that you could adjust these empirical end parameters in order to make the model adjust to some measurements. Now, the model can deal with hydraulic structures such as culverts, gates, weirs, and bridges. And these are typical structures that the model can handle, as we will see. So we have a specific exercises and presentations that will explain you how to use culverts, how to use gates, how to use weirs like this or like this or like this, and how to use bridges. So these are all part of the hydrobead flood system. Now, the model will give you results. Every run you will get results. Now, the question you should ask yourself is, can I trust the results I'm getting? Well, the answer to that, it's simpler if you would be able to calibrate or validate the model. So there are two processes that are called calibration and validation that allow you to increase the reliability of your results. Now, in order to perform a calibration and a validation, you need data, and sometimes in many places there are no data available. So in those situations, what we recommend is to perform a sensitivity analysis. So if you are not certain over the Manning-Sen parameter, what you could do is to make several runs with variation of parameters, and that's something very simple to use in the Flow2D system, because you can make a run by multiplying all the Manning-Sen by a factor, 1 point, let's say increase by 10% or 20%, or decrease it by 10% or 20% or more, and compare the results. And you would have a sense of how different the results are by varying that parameter. So that's something that you could do if you don't have the data. But if you have the data, it's highly recommended to calibrate and validate the model. Now, what is calibration and validation? Well, the model is not the real world. The model is an approximation of the hydraulics and hydrology of the real world. That's what hydrobid flood is. It's an approximation. It makes some assumptions. It runs very stable. It's very accurate, but it's an approximation. It's never the real world. Now, in order to bring it closer to the real world, you should ideally perform these two processes. So, in general, you have a conceptual model that tries to represent the reality, and then you build a computerized model like hydrobid flood that hopefully with a computer simulation would reproduce the reality that you want to analyze. So that's something that is a general process of creating a programming, by programming a computer model. Now, in order to make a reliable computer model, you need to verify the model itself, the code, the programming that you do to create this computerized model. And this is called a verification, where in the verification process, we as developers determine that the program accurately represents the conceptual model. So it solves correctly the equations. Now, this part is done. You don't need to worry about it. We ensure that the hydrobid flood computational model has been verified, and it runs and it correctly solves the equations. So don't need to worry about verification. Now, calibration is the first step that you would do when you apply the model to a specific project. So in this process, you adjust the numerical or physical parameters such as Manning-Sen roughness coefficient, so that the program, the hydrobid model in this case, would improve the comparison with the data that you have. And this data can be watermarks of a previous inundation. It can be measured velocities or depth for specific events. It can be a wide variety of things that you could use to calibration. Now, what you do is you adjust the model, you compare, and you continue adjusting until the comparison is satisfactory. And when it is satisfactory, then you consider that the model is valid, is calibrated. Now, the second step that is also ideal, because you would need for that a second data set of maybe a different event, different from the one you use in the calibration, where without moving your parameters, so keeping the same parameters like they are, you try to replicate this different event. And in so doing, you ensure that the results of the validation compare very well with the data of this independent data set. So these two processes, validation and calibration and validation, are ideal because if you are able to perform both, and you have the result, the data to support that, then you ensure that the model is able to reproduce and predict many different events in your project. Again, if you don't have enough data, that's okay, because many places we don't have the data, and in those cases then you would need to do the sensitivity analysis as I suggested before. This is a typical application of in a calibration process where we use a river flow 2D, which is the engine of oil flow 2D. I'm sorry, I meant to say hydrobid flood. Oil flow 2D is another model that we developed, and this is a comparison with data. You see the point. This is a flow in a river. This is the bed of the river. These are points that were measured by topographic survey of the water surface. And this is a comparison of a hairgrass model results shown here in this continuous dark blue line, and the river flow 2D results in this light blue line. So this is what gives you assurance that the model can predict flow in rivers, for instance. Okay, so getting more into the conceptual model in hydrobid flood, the traditional approach of hydraulics and hydrology has been over the years to use a separate computation for the hydrologic components. So you apply a hydrologic model to determine runoff and losses for infiltration, and then you apply this to the watershed and obtain here in this lower part of the watershed inflow hydrograph to the lower part of the watershed, where you apply a hydraulic model to determine maybe flooding on this urban area, etc. So it's a combination of two type of models, a hydrologic model and hydraulic model. Now, presently, more and more, there is almost no need to separate the hydrologic and the hydraulic processes. And then the trend is to use an unified or integrated approach where you model hydrology and hydraulic simultaneously, and you don't separate. And then we have an integrated hydrologic and hydraulic model that will compute the runoff, losses, flood, and also the hydraulics of the routing downstream with all the structures and so forth. This is exactly the approach that the hydrobid flood has followed. So the hydrobid flood is essentially a hydrologic two-dimensional model. It's an integrated hydraulic model. Now, in terms of capabilities and performance, the model uses a flexible mesh. It's high performance because it can use GPUs, as we will see, to accelerate the computations with multiple processors. And it works in SI or English units, or imperial if you want to use the term. It uses QGIS as the main graphical user interface. In terms of numerical calculation engine, it uses finite volume method, which ensure exact volume conservation. So the model does not numerically eliminates or creates mass or volume. So it conserves the volume exactly. It can handle dry and wet beds, supercritical and subcritical flows, so very rapid or very slow flows. It has components for rainfall and infiltration, bridges, culverts, dam bridge, gates, and weirs. We will see many of them during the course with practical exercises to each of them. And it has also modules that we will not have time to cover them, but you need to know that the hydrobid flood system includes sediment transport module, and this will be a a topic of a future course if necessary. Now, I mentioned briefly before that Hydrobead flood uses river flow 2D as an engine. River flow 2D is a commercial model that is developed by Hydronia, and it has many other features that are not present in Hydrobead flood, including mud and tailings flow, so it can model the break of tailing dams. It has a water quality module. It can do oil spills on land and water, and it has a plastic particle transport module as well. Now, the Hydrobead flood is provided at no cost to anybody that would be authorized by the Inter-American Development Bank to use it. So if whatever organization in the government would like to use the software, you just need to write to the proper Inter-American Development Bank person that we can provide that information to you, and then request a license, a permanent license of the model. I need to say that the license used in the training courses is temporary, but anybody requesting the permanent license after the time that it expires will be able to have that permanent license authorized by the Inter-American Development Bank. So, in essence, Hydrobead flood incorporates most of the feature of the river flow 2D model. It's supported by the Inter-American Development Bank and is, for the most part, accessible for IDB finance projects. Also, universities form part of this project. So if any university would need to use the software, they can request that too. Now, getting more into the details of the model, the flexible mesh is probably the main characteristics of the Hydrobead flood. And the flexible mesh, as I mentioned, is a triangular irregular network that contains triangles. And in the model, you will see all the tools that are available to generate this type of mesh. The mesh can have internal holes, like you see here, and can be refined in areas where you need more detail. So all of these, you will be able to do it interactively in the exercises. Now, the main computational unit of the model is the triangle. And at each triangle, the model computes the depth of flow, the components of the velocity, and the elevation of the bottom if it changes in time due to erosion or deposition when using the sediment transport module. Now, the velocity can acquire any direction depending on the computation that you get, so there is no restriction on the velocities that the model can handle at any given triangular unit. Okay, so why the flexible mesh is important? Well, this is an example of two approaches that are typical in two-dimensional models. On the left, we have a Hydrobead flood mesh around a gated structure. So here are pillars that represent the main structure of the. There will be gates in between these pillars here, and we are interested in looking at the flow around this area. So with the flexible mesh, you see that the mesh can adapt to this irregular geometry, the round areas here, this very small sections over here, and it can be refined around this area and less refined in other areas where you don't need that much detail. Now, on the right, what you see is a square grid 2D model. There are models that use finite difference method mainly, and they use a square grid. And the square grid is formed by square cells instead of triangles, and they cannot be adapted to irregular geometry. They just give you a staircase approximation of the different boundaries. And if you want to refine, the only way to do it is by reducing the size overall. Now, reducing the size is possible, but then you would end up having a much bigger mesh or grid with many more points to calculate, which makes the model run much slower. So in this particular case, we were able to generate a mesh that covers everything with the adequate resolution that was required around this structure with 4,100 cells. Now, the same mesh or grid in this model would have required 2.2 million cells, square cells. And that was much more expensive from the computational point of view than this one. So that's one of the issues of the advantages of flexible meshes. Also, the accuracy is obvious when you look at a detail here. If you want to look at the flow in this thing and see how the flow interacts with this boundary, it would be very difficult to replicate that with this type of grid. So in general terms, the 2D mesh or flexible mesh is much more realistic to represent irregular terrain. And that's one of the reasons that we use that in a hydrobid flood. Now, as I indicated before, the model can handle culverts, and the culvert calculation is done using the USA Federal Highway Administration formulation. It can do circular and rectangular cross sections, and there will be an elliptical section that is going to be incorporated, and it's under development. And also there will be a culvert component that will be calculated using the EPA SWIM. Now, we will cover EPA SWIM in this course because the hydrobid flood is integrated with the EPA SWIM. The EPA SWIM is a model developed by the Environmental Protection Agency of the United States that was developed to solve the flow in stormwater systems. So the hydrobid flood integrates that model dynamically within its computation. So you could use that model also to compute culverts if you wanted, or the complete stormwater system, as we will see in one of the exercises. Now, the model can also handle weirs, and the weirs can be vertical walls or it can be embankments. They can be over top, and the model computes the flow over the top of the weirs. They can vary in crest elevation. So if you have a survey of the weir crest, the model can use that to represent how the crest elevation of the weir changes along its structure. The model can handle breaches of many different forms. Virtually any form of breach can be considered. Arcs, the breach can overtop. You can calculate the flow by the pressure flow and the overtopping, and that is very important because that helps improving the design of breaches, or at least understanding what can happen if the breach is overtop in a flooding, and how that can exacerbate the flood upstream due to the backwater effect that it can create. There are many ways to handle breaches. We will cover this in a exercise and a presentation that we have specifically for that, but we can create the piers specifically and then calculate the flow around the piers, making the piers be part of the mesh, as you can see here. Or you can just use the bridge component that simplifies how the bridge is computed, or combine both options as well. The gates component is also useful. We'll see that how to use it, and you can have gates of in all the different states of flow. And probably one of the most important components of the model is the hydrologic component, because it makes the model computes or behaves as a distributed model where you have rainfall that can vary in space and time throughout the watershed. And you can have precipitation and evaporation that represents how that variable change in all the space. And the infiltrations can also be variable in space, and you have three methods to compute it: the Horton, Greenamt, and SCS curve number method. Now, it's important to understand that the hydrologic component of river flow 2D and hydrobit flood is meant to be used as to model events. So it's not a continuous model. We don't pretend the model to be used for continuous simulation, like something to model 3 years of a watershed or something like that. It's meant to compute hydrologic events of hundreds of hours or that range. So the reason that that's the case is that the model does not account for groundwater. So there is no way, when you compute the infiltration is treated as a loss, and in that sense there will be no return from the infiltrated water into the main river. So that is a good approximation, provided that you're modeling events and you're modeling relatively short-term simulations. There is a component for internal weir or dam breaches, so you can represent how a dam or a weir breaches and what the resulting inundation that can generate. This is the use of the sediment transfer module to represent how a dam body erodes, and this is how something that you could use also to model a dam breach. So in this animation, what we see is the velocity. It's indicated in colors, and you see here that the initial state of the dam, let me show it here. This is the dam crest, and it's being overtopped by the reservoir that is here, and as it gets overtopped, it gets eroded and it breaks, and the sediment is traveling downstream as well. Let me put it again. You see the high velocities here indicated in red, and the complete erosion of the dam that occurs in time. You can do all this. This was done actually by applying the hydrobit flood model. Now, the hydrobit flood uses or can use GPU cards. The GPU cards are video cards that allow the model to run in multiple processor mode. Nowadays, we have cards that have more than 10,000 processors. That's the case of an NVIDIA 3090. And so any NVIDIA cards can be used to run the model, and that allows the model to run much faster. You can use cloud computing as well. You can install the model in a cloud like Google Cloud and that will also help the model run much faster. Just so you have an idea, these are some of the cards that are available on Google Cloud. The Tesla V100 is at the present date one of the fastest cards available, and it has 5,120 processors. So that you understand how fast the model can run with a GPU card, this table represents a test that we ran some time ago to compare run times between different GPU cards, and in the test use it with different meshes. So we have the same case running with a mesh of almost 20,000 cells, another mesh of 154,880 cells, and the large mesh that has 1.8 million cells. We run the three cases using only CPU. CPU is the simple processor that you have in your computer, and we use one core. So this cell took, this is time, this is 8 minutes and 14 seconds. This mesh took 3 hours and 23 minutes, and this one took 8 days and 23 hours. So look at the increasing time using CPU. Now, I won't give you all of these numbers, but I'll give you the last one, which is the shortest one, with the Tesla V100 running in Google Clouds. Now, this mesh of 1.8 million cells that took almost 9 days to run in a single CPU computer took only 18 minutes to run in a Tesla V100. That's an acceleration of 687 times. So this is the type of acceleration that you can expect using advanced GPU cards. And all of this is part of the Hydrobit flood system. It's available if you have the proper hardware. The model can run directly in any one, and then the same setup, data setup that you make to run in a very small model, just change the card or the computer and it will run that fast. Many people ask in that regard about how fast or how does Hydrobit flood compares with other models. And I'm going to present you now a comparison based on the UK benchmark test 5. UK Ministry of Environment created a set of benchmark tests by which anybody can have access to the different data sets to compare two-dimensional models. So what we did was to take one of these tests, which is test 5, corresponds to a dam break, and run it and compare it with other models to see how fast the Hydrobit flood was. So the objective, in general objective of the test is to check the ability of the model to simulate flooding generated by the rupture of a dam in this case. So there is a dam here, idealized dam in this red spot. Then you have a river that goes downstream and then enters this other river here. Initially, the river is dry, and then you have points to compare results at these points over here. So you have an inlet hydrograph set here, and this is the profile of the river along this green line. So it comes from 200-meter height here to 150 approximately here. So these are the run. This indicates depth of flow. So you have, again, you have flow coming from the dam here, getting into the river downstream. So this is a comparison of times with HEC-RAS 2D. This is HEC-RAS 2D, and RH2D, which these are two US generated developed models. They are free, and we wanted to compare computer times. So what you see here is the runtime with different cards. This is Riverflow2D, that is the engine of Hydrobit Flood with one CPU. It takes 0.06 hours, and this is with 8 CPUs. This is with a GPU 970. You see the change here. It's one order of magnitude already. This is another GPU card, and this is HEC-RAS, and this is another HEC-RAS result with different time steps, and this is SRH2D. So for this particular test, HEC-RAS was much slower, and actually Hydrobit Flood was between 12 and 40 times faster than HEC-RAS2D, and it was 217 times faster than SRH2D. Also, the same comparison with Mike 21, which is a commercial model as well. It resulted in 24 times faster than Mike 21, and these are the computer times that you see over here. It's 40 minutes, and this is a different test, but with different mesh. But it took, instead of 40 minutes, 1.6 minutes in Hydrobit Flood. Now, the second part of the presentation is about the graphical user interface. It's just an introduction because we will have time to go over the details of this user interface. So, as I mentioned, the user interface is based on QGIS. This is a geographic information system that is compatible with other geographic information system that but in this case, this is open source and it's used worldwide and it's free distribution. So you are free to install this in any number of computers. Actually, the installation that we provide for Hydrobit Flood includes already QGIS 3.16. So you don't need to install the software separately. It installs directly when you install the complete system. This is the main user interface. You will see that you have a flood, Hydrobit Flood toolbar with different icons that you see here. You will have a layer panel. You will have a map area here in the status bar. And this set of icons will help you access different tools that we'll use in the Hydrobit Flood system. For instance, this is to open a project, this is to create a mesh, this is to export the data, this is to make graphs, this is to make animations, this is to make cross sections, and this is a general tool icon. So in general, the process that you followed, or the workflow that you follow to create an Hydrobit Flood application, is to create a new project using the Hydrobit icons. You create the meshes that you need, and you enter the projection. This is very important. From the get-go, you need to enter the projection. So you need to know what is your projection of your data. And you enter your project directory. Then, in this case, we load a DEM, a digital elevation model, that are indicated by these colors here, indicate the elevation of the river bed and the floodplain. Then we enter the domain outline polygon, which is the extent of the model area. We create a mesh, and again, all the tools to create this mesh are included in the Hydrobit Flood system. The mesh can also be refined in many different ways. In this case, we are refining the mesh along the main river. And then we enter boundary conditions that include the inflow and outflow areas. And once that's done, then we output the results, and then we enter the simulation time, the output interval, and many other information that is dependent on the components we use. You see here all the components that are available: rainfall, bridge, piers, culverts, internal rating tables, dam breach, sources and sinks, etc. And we run the model with this button here. We run the model, and then we see dynamically how the model runs. So when the model runs, you will see this window appear, and you will see dynamically the colors in this case, the water depth, how it evolves in time. So you will see this evolution in time. You will see the volume error. See, the volume error will be all the time in this range. This case is 8.25 to the minus 14%. So it's a very, very, very negligible error. Inflow, discharge, outflow, discharge, time, step, use, and many other information that is provided here dynamically. Once the model runs, then you can create a number of maps and animations. I will show you some examples of that to finalize. In this case, I created, this is a type of map that you can create with the model. In this case, this is time to the arrival time of the flooding. So you can create arrival time, or the time, the inundation duration. There are many parameters that you can plot in time to depth maps. You can create flood hazard maps using different criteria of different countries. You can create cross sections and animate the cross sections. So this cross section you extract from here, and you can see the velocity and the depth of flow along this line, or a profile as well. You can create velocity maps as magnitude. This is a hydraulic structure, and this indicates the velocities in module at different locations, and this is the scale indicated here of the velocities that you get there. You can create animations, as you see here, to look at the eddies that can be formed along the structures. That can be important for hydraulic structures or for bridges, for instance. The model has also a pollutant dispersion component that you can use. This is a spill of pollutant over here, and you can see the concentrations of the pollutant in that structure. You can represent three-dimensional meshes as this one here. This is a hydraulic structure with a spillway and gated structure here, and generate this type of traces. These dynamic plots that show the velocity field with indicated in colors with the high values, indicated in red, where you see the high concentration of velocities and the flow patterns. Well, this is just an overview of what we will be doing during the training. So again, it's a general overview. We have specific presentations for all the components. Later today, we are going to be having the start of the course with the GIS Introduction to Graphical Information Systems. But so far, I just will stop for now, and be happy to answer questions you may have.